Hello everyone, welcome to ORgano. So this is our conceptual problem solving part. Now here I am taking a question, the question which was came in GATE 2015. Okay, so the question is, the major product formed in the following reaction is. Now you have given a substrate of a kind of phenol derivative, and the reagent which is used is sodium hydride and this kind of allyl halide, and you have to identify the K, and then you have to identify the L by using the reagent which you have given to you, that is number one, that is heat. Okay, delta sign, that means it is a heat, and the second step, that is PDCl2 CuCl2 O2, that means this is your Wacker oxidation. Okay, so now we all know that the sodium hydride takes a proton from here and it will generally attack to this halide. Now the question arises that this negative charge, from where this negative charge will attack. Either it is in this conjugate site, like in this negative charge is directly attacked to here and these bonds go here and this will leave from the system, or either this negative charge directly attack to this center and this seal will leave. Now for this question you have to know and you have to identify the difference between the you have to know the difference between the Sn2 or Sn2 prime reaction. Okay, so what is Sn2? We all know that, but here is a one term is arise, that is Sn2 prime, so that you need to know. Now see what is Sn2 and Sn2 prime and then difference between them. Now see, if we take generally if we take this allyl halide, this is your allyl halide. Okay, so this is your allyl halide. Now if we use generally like any kind of nucleophile, that is, say I am saying it is like nucleophile, or it is say like X minus. Okay, so this X minus directly it can attack over here or directly attack over here. Now there is we all know that if in the case of Sn2 reaction there is a possibility of directly attack over here and this will leave from the system, and you ultimately you can get this type of product. Now we all know that Sn2 reaction is backside attack, so if the bulky group is present on here, then it will not attack to this side. Now what is the concept of this reaction? This nucleophile comes with its own HOMO, and here this leaving group it has a LUMO. So LUMO means it is a sigma star of this Br bond, that is the sigma star of this CBr bond. Okay, that is CBr bond. Now see this sigma star, now this negative charge, that is it contains its own HOMO, and here you have the LUMO of this CBr bond, that is your LUMO. Now this HOMO-LUMO interaction, you can ultimately get this type of product. Now see, there is one more concept arises, that is Sn2 prime reaction. Now how can you identify when the Sn2 reaction will occur, when the Sn2 prime reaction will occur? Now see, what is Sn2 prime? Now Sn2 prime is nothing but this is your Sn2 reaction. Okay, this is your Sn2. Now what is Sn2 prime? Now if we take this same compound like this, then if the nucleophile, or saying it's an Nu minus, this electrophile directly attack over here, these bonds go here and this will leave from the system. So this is your Sn2 prime type reaction. Okay, so this is your Sn2 prime, which is written over here, this is your prime sign. So this is your Sn2 prime type reaction. Now see, now there is also this double bond, C double bond C has a pi star orbital, and there is an interaction between this pi star and the sigma star, then after the formation of this type of product. Okay, so now how can we explain it? Now we can say it that in this way, if there is a HOMO of this bond, this is your double bond, this is your part, and this is your Br, this is your bond, and this is your ultimate bond over here. Now see, this is one, this one. So you have to consider this nucleophile has a HOMO and this system has your own LUMO. So this is your interaction between HOMO-LUMO interaction. So similarly there is this is your pi star, this is your pi star, and this is your sigma star. So there is an interaction between, and there is a chance, so there is a formation between this pi star and sigma star. It will combine with each other and they will form a lower energy orbital, that is this one, this pi star and sigma star, and this will, after the construction of this type of bond, and there is a formation of this final product that you get, this like this one. Okay, So this is your overall Sn2 prime reaction. Okay, so this is your LUMO, and this nucleophile is comes with its own HOMO, and there is a interaction between HOMO LUMO, and ultimately you can get the final product. Now see, when the Sn2 reaction occur, or either Sn2 reaction or Sn2 prime reaction will occur. Now see, for this you have to know few concept. That is, if we take a compound like this way, like this, Pr over here. Now this is generally called prenyl bromide. Okay, prenyl bromide. Now there is a one more important concept, is that this is not allyl. Okay, allyl is only said that only call when this double bond is not substituted. Okay, so this system generally called the allyl. Okay, this is your allyl, not prenyl. But when this type of this CH2 is directly this CH2 are substituted by this others group, then the different types of names are arises. Okay, so in this case these two hydrogens are substituted by these two methyl group, then it is called prenyl bromide. Okay, so for this only allyl is only said when that this type of group substituted by no substitution is occurred, then only two hydrogens is present. So this is called your allyl group. But when these hydrogens are substituted, then that is called your this prenyl bromide. Okay, here these hydrogens substituted by the methyl group, and these two are called prenyl bromide. Okay, now we all know the nucleophile. If the nucleophile directly attack over here, you get the final product like this. This is your Sn2 pathway. Okay, we all know that. But when this type of compound, this Nu minus directly attack over here, and this will leave. This is your Sn2 prime, and ultimately this is your Nu. Okay, so ultimately you can get this one, but this process doesn't happening. Okay, so this is not this type of compound generally not follows this Sn2 prime reaction, just because of if these hydrogens are these two are so this is your unsymmetrical alkene system. Okay, so in case of unsymmetrically substituted compound, just because of these two are methyl substituted, but here is the only hydrogen is present. Okay, so this type of this is unsymmetrical. Okay, unsymmetrical. So this type of unsymmetrical compound generally follows the only Sn2 pathway, not the Sn2 prime pathway. Okay, the Sn2 prime pathway only follows when the both sides are symmetrical, or that there is no bulky groups are present. So if there is a two bulky groups, so this will not attack directly to this center, and this will not go over here, and so this process is not followed over here. So that is why the Sn2 reaction is generally followed for this reaction. So this is the difference between the Sn2 reaction and Sn2 prime reaction. I think you can understand over this all those things. Okay, now let's come to the problem. Okay, let's come to the problem that you have given, that is this one. It's a methyl group. This is your OH, and first you have given the sodium hydride. So we all know that this hydride generally takes a proton, just because of this phenol hydrogen is sufficiently acidic. So that is why this hydrogen is generally takes up first, so it gives the negative charge, and after that now you can easily understand that which type of addition will occur is either Sn2 or Sn2 prime. So this is unsymmetrical, so this is your prenyl chloride, this is your prenyl chloride. So this is your unsymmetrical, and this is your bulky. This side is not hindered, so this side will this negative charge directly not attack to this center, so it will directly attack to this center, and this Cl will leave from the system. Okay, so ultimately what you can get after this reaction, this is your Sn2 reaction, not your Sn2 prime. Keep in your mind that. Okay, so this is your methyl, this is your O, these bonds go over here. Okay, so this is your final product. Now this is your K. Okay, so find the when the given option, that is which is your K. So this is not your product, this can be your product, or either this can be your product. So D is not up, so you can easily eliminate option A and option D. Okay, so your either option B or option C will be correct. Now let's find the option. Let's find the L, structure of L. Now you have given the heat. Okay, Now see, there is a possibility of 3,3 sigmatropic reaction. How? I will show you how the 3,3 sigmatropic reaction will proceed. Now this is your 1, this is your this is your 1, this is your 2 and 3, and this is your number 1, this is your 2 and 3. Now see, this is your 3,3 sigmatropic reaction. This is your 3,3 sigmatropic. Okay, so this is your 3,3 sigmatropic reaction. Okay, now see how the 3,3 sigmatropic reaction will occur. Now this double bond will attack over here, these bonds go over here, and this will go over here. Now see, this is how the reaction proceed. Now see what will be your product. Now after that you can get this type of product. This is your double bond, this is your methyl, this double bond, 2 group, and this one. Okay, so this is your product. Now there is a possibility this is dearomatized, so it will generally try to get back its aromatized form. So this hydrogen leave from the system, it will tautomerize, that is your tautomerized form, and it will generally get back to this aromatized form. Okay, so this is how your product form after the heating. Now we have given the final step, that is Wacker oxidation. Okay, so I think we all know that what is Wacker oxidation and how the Wacker oxidation reaction proceed. So the reagent which is given to you, that is PdCl2, CuCl2, O2 and H2. We all know the mechanism. So if you haven't checked that video, I will put the link over here, and you can go and watch those videos. I already made a video on Wacker oxidation, or anything, I will cover, trying to cover all the oxidation reaction topic. Okay, so this is your Wacker oxidation. So this is your Wacker oxidation. Okay, now what will be your product? That we all know that this type of alkene generally form the terminal alkene, generally form the ketone, methyl ketone. Now what will be your product? This type of compound. Now we all know the final product, that is your terminal alkene generally gives a methyl ketone. So this is your methyl ketone and this is your terminal alkene, so it will generally form this double bond, that is ketone, and we get the ultimate product which is given to you, that is your L product. Okay, now let's find your answer. Now you have left the option B and C. So this is not your product, so this, just because of this double bond, there is no 3,3 sigmatropic rearrangement, and there is directly occurring this ketone over here. So this product is not your answer. So the final option that you left is option B. Okay, so this is your final option. You can get the methyl ketone in the this terminal alkene conversion, terminal alkene to methyl ketone. Okay, so this is very much important for you guys, and I hope I covered all those topics related to this Sn2 or Sn2 prime, and I think I can easily you can easily understand all those topics, and I think you can differentiate between the Sn2 and Sn2 prime easily. So I hope this video is very much useful for you. Thank you so much for watching.